Hello students, we shall proceed further with our discussion on instruction set. In the last class, we were discussing on the branch control instructions, or what is called as the jump instructions. We have completed the unconditional branch instructions. Today, we shall try to cover the conditional branch instructions, iteration control instructions, call instructions, and if time permits, we will pass on to BIOS int 10H programming. Now, just to brief you what we discussed in the last session, the different types of jump instructions include conditional jump instructions, unconditional jump instruction. Conditional jump instruction has the categories like short jump and they are basically a relative jumps. Unconditional jump instructions includes short jump, near jump and far jump, where short jump always uses a relative addressing, or they are say basically a relative addressing address calculation concept. Near jump addresses or near jump instructions uses direct mode and indirect mode addressing, and then far jump basically calculates the address say based on direct and indirect. Now, the short and near jump say are always intra-segment jumps, and your far jump is an inter-segment jump. Now, what is meant by inter-segment and an intra-segment jump? Inter-segment is something where the control of the execution gets transferred from one code segment to another code segment. Say intra-segment is something wherein which the control of execution will be present in the same code segment. Now, this is all about the unconditional say branch instructions. Say today we shall proceed further with conditional branch instructions. And my dear students, remember, conditional branch instructions are always short jump. So if it is a short jump, obviously they are intra-segment jumps. So generally we don't have say inter-segment jumps with respect to conditional jump instructions. Now, what is this conditional jump instruction? What is the difference between unconditional jump instruction and a conditional jump instruction? The name itself specifies conditional jump instructions are those where based on some condition branching will happen. The control of execution gets transferred to a target location based on satisfying a particular condition or for a non-satisfaction of a particular condition based on the instruction. Say for example, the syntax of conditional jump is something like jump condition to the relative addressing, where the relative address is an 8-bit number. It is called as relative address, as I mentioned. The condition is basically user specified condition. The instruction alters only the content of IP. Why instruction alters only content of IP? Why does not it alter the content of CS? It alters only content of IP and does not alter the content of CS, because always your conditional jumps are short jumps and they are intra-segment jumps. Hence, microprocessor jumps within the same code say of the segment memory where it is an intra-segment jump. Now, let us quickly pass on to the conditional jump instruction operation. Microprocessor initially checks the specified condition. If the condition is true, microprocessor performs the jump or branch operation by adding the given relative address to the contents of IP. So, the IP value gets changed something like this. So, IP will be added with the relative address if the condition specified in the instruction is true. If the condition is false, the microprocessor does not perform the jump operation or jump instruction, or it will not go to the jump location. So, IP contents are not altered, so that say IP will be pointing to the next instruction after the jump instruction in the program. So, as usual, your processor will proceed with the next instruction after the jump instruction. Now, let us pass on to the list of conditional jump instructions for unsigned operation. Underline this word, unsigned operation. Operand 1 is equal to operand 2. What is the instruction? I want to compare two operands, whether contents of AX is equal to content of BX, say for example. So, in that case, I will use an instruction like jump if equal to the relative address. So, if I say that jump if equal to down, where before this I would have used say compare AX comma BX. Assume that the content of AX is 4000, content of BX is 4000. So, 4000 is equal to 4000, what will happen? 0 flag will be set to 1. Now this 0 flag is checked here. So jump if equal, it is also called as jump if 0. So once jump if equal, say if there is a setting of 0 flag by the previous arithmetic or logical operation, then say the control gets transferred to the relative address, and that relative address will be somewhere here, say down. Now what will happen is IP will be pointing to the next instruction here. So this is the next instruction. But when the condition is true, say for this IP, this displacement that is down, say is added, so that IP will point to this location where I will have some instruction X here. That is how basically your jump operation happens. And remember, whenever we perform the jump operation, say that should be preceded with some arithmetic or logical operation, or generally it will be preceded with a compare instruction. Now in this case, say I am trying to check the 0 flag. So using jump equal instruction, if the 0 flag is set to 1, if the condition is true, jump is performed, otherwise no jump is performed. Second one, I want to check the condition whether operand 1 is not equal to operand 2. Jump if not equal to relative address. Jump if not equal to relative address means, say if the 0 flag is not set, see this, if the 0 flag is not set, then the condition is true, then there will be a jump, otherwise there will be no jump. It is something like this. I want to check the inequality. So I will again say compare AL comma BL. If they are not equal, jump if not equal to. I just use a label not equal. So here I have a label not equal where I will say display something. I'll display something. So here what will happen is, if the condition, say that is the 0 flag is not set, then I'll go to not equal. Then operand 1 greater than operand 2, that is jump if above, underline the word above, jump if above to the relative address. That is, if carry flag is set to 0 and 0 flag is set to 0, say the condition say will be treated as true, jump occurs. Otherwise, if carry flag is set to 1 or if 0 flag is set to 1, the condition is false, no jump. Now why are we trying to check the carry flag? The reason is, say compare is a logical subtraction, it is a non-destructive subtraction, where when I compare AX comma BX, if the AX content is greater than BX content, in that case carry will not be generated. So once the carry is not generated, then the condition automatically becomes true. So that is how you should be able to understand jump if above. Next, if operand 1 is greater than or equal to operand 2, jump if above or equal to relative address is the instruction that we basically use here. Now, so this will be true when CF is equal to 0. So when CF is equal to 0, the condition is true, jump happens. When CF is equal to 1, condition say is false and no jump. Operand 1 less than operand 2, jump if below relative address. So if CF is equal to 1, condition is true, jump happens. If CF is equal to 0, condition is false, no jump happens. Now here, when we are trying to check the inequality or less than or greater than, say basically here for unsigned numbers, we use the above and below for unsigned numbers. For signed numbers, we use greater, lesser. So here we use A and B to represent this conditions. Now, jump if above or equal, jump if below or equal. Say perform the jump operation when the condition is below or equal. What do you mean by below? Below means carry flag is set. So when the carry flag is set to 1 or if 0 flag is set to 1, then the condition is true. Say otherwise, if carry flag is set to 0 and 0 flag is set to 0, condition is false, there is no jump. List of conditional jump instructions for signed operation. Now the previous case was for unsigned operations, and now we'll proceed further with signed operations. What do you mean by signed operation? When your operands are signed numbers, then we will be using these conditional jump instruction. If you carefully observe, say we'll say jump if equal. Jump if equal is used to check whether operand 1 is equal to operand 2. When operand 1 is equal to operand 2, we use jump if equal relative address. Say if the 0 flag is set to 1, then automatically jump happens, otherwise no jump happens. Operand 1 not equal to operand 2, jump if not equal. Operand 1 greater than operand 2, jump if greater. If you carefully observe, in the previous case it was, see this, it is jump if above for unsigned operation, and same thing here in the signed operation, say we will be using say jump if greater. So there it is above, here it is greater. So if operand 1 is greater than operand 2, say if you want to check such condition, I will be using jump if greater instruction JG relative address. If the condition is true, say jump happens, otherwise no jump happens. Same thing. Operand 1 greater than or equal to operand 2, jump if greater or equal. Say operand 1 equal less than operand 2, jump if less than say relative address. Operand 1 greater than or equal to operand 2, jump if less than or equal to relative address. So here if the condition is true, jump happens, otherwise if the condition is false, no jump happens. So everything is something similar to unsigned operation. Only thing is here instead of above and below we will be using greater and lesser. Carefully observe this. So here I say JGE, there I was saying JAE. Now we have another set of conditional jump instruction based on flags. Here is a list of instructions. Some of the instructions works for carry flag, some of the instruction works for 0 flag, some of the instruction works for say sign flag, parity flag, and so on and so forth. Now jump if no carry to relative address. If the carry flag is equal to 0, the condition is true, action taken by the microprocessor is it performs a branching operation. There is a jump. Jump if no carry to relative address. If carry flag is equal to 1 and if I use this particular instruction, then the condition is false, no jump. Sir, when do we use this? Say for example, I will say add AL comma BL, jump if carry to down. After addition, if there is a carry, then this condition becomes true. This instruction results in a branching operation. If there is no carry flag is set, then it proceeds further with the next instruction. So I have some instructions here. Now down is somewhere here. So if the condition is true, then automatically processor comes and executes the instruction present here. Remember my dear students, if you check all these examples, say all of these branching instructions have been used after an arithmetic or logical operation. Now carefully observe, here I have used a compare, here I have used a compare, here I have used an addition. So see, only after arithmetic or logical operation we are trying to use this conditional branch instruction, because in the conditional branch instruction we are trying to check the flags, we are trying to check the flags, we are trying to check the condition of the flags. Since we are trying to check the condition of flags, say condition of the flags are affected only after the arithmetic or logical operation. So that is the reason why only after an arithmetic or logical operation I need to use these conditional branch instruction. Suppose if you ask me a question, sir, if I write a program something like this, what will happen? Move AL comma BL, jump if carry down. So the syntax is 100% right. So you have some instructions here, you have some instructions here. Your assembler will not show you any error, because this is a logical error. See what is happening here, say move AL comma BL, move AL comma BL is a data transfer instruction. Say after this data transfer instruction you are trying to check the carry flag. However, for all the data transfer instruction your flags are not affected. So if I check the carry flag in this scenario, say the carry flag which is being set for some other arithmetic operation which is happened prior to this move instruction will be considered here. So you should be very careful when using this conditional, say, jump instructions. Now, jump if parity, there is something called as parity flag. What is parity? Say, it indicates the even number of ones and odd number of ones present in the obtained result. Say, after performing an arithmetic or logical operation, if the obtained result has got an even number of ones, then parity flag will be set to 1, otherwise parity flag will be set to 0. Say, if I want to check the parity flag, then I'll use something called as JP relative address. Say, remember this P represents parity. If parity flag is equal to 1, the condition is true, jump happens. If parity flag is equal to 0, for this instruction, the condition is false, no jump happens. Now, jump if no parity. Sometimes I want to make the change in control of execution or flow of execution when there is no parity. Then after my arithmetic or logical operation, instead of using JP, I may be using JNP. And remember, my dear students, all this condition checking is based on the requirement of the program, requirement of the user program. So it is left to your credibility, left to your credentials, say how to use, when to use these instructions. So that is the reason I always keep telling you that the hold on the instruction set makes you very much comfortable in writing assembly language programming. JNP, jump if no parity. If it is false, no jump. If it is true, there is a jump. Next, JNS, JS works for sign flag. JNS relative address, jump if no sign. So if the sign flag is equal to 0, so sign flag is not set. That is what is the meaning. So the condition is true, jump happens. But for the same instruction, say it will check the sign flag, say if the sign flag is set, the condition is false because I am checking for not sign, that is no sign, but sign flag is set here, then no jump. Similarly, JS, jump when the sign flag is set. So when the sign flag is set, it is true, jump happens. Say here in this case, say the scenario is the flag status, it is SF is equal to 0, so false, no jump. OF is equal to 1, jump on overflow. JO, O represents overflow. If OF is equal to 1, true, jump happens. So JNO, jump on no overflow. If OF is equal to 1, say condition is false, no jump happens. JNO, OF is equal to 0, condition is true, jump happens. Next, we have another very important branching instruction, which is a conditional branching instruction, what is called as JCXZ to relative address. This is a conditional jump instruction where microprocessor checks the content of CX register. If the CX contents is equal to 0, microprocessor performs the jump operation by adding the relative address to IP. So basically we use the CX contents, say, for checking. So if the CX content is equal to 0, what will happen? The 0 flag will be set. When the 0 flag is set, then automatically branching will happen. If the CX contents is not equal to 0, microprocessor does not perform the jump operation. Let us move on to the next set of instruction, what is called as iteration control instruction. What is this iteration control instruction? The name itself says iteration. If you want to repeat a particular operation, set of instructions, if you want to repeat set of instructions for more than one time, then we need to go for some iterative, say, operation. So to facilitate that, we need iterative, say, control instructions, and it is something similar to your for loop in C programming language. Now, how does this work? There is a very important instruction, what is called as loop instruction, loop relative address, where loop relative address or loop if 0 relative address. So here loop if equal, carefully observe. Next, loop if not equal or loop if not 0, both means the same. I can use them, say, interchangeably. Here also I can use them interchangeably. So the different iterative control instructions are loop if equal or loop if 0, or loop if not equal, loop if not 0. Now let us see one by one. Again, I would like to press upon this point. These instructions are basically used for looping control or iterative control. loop relative address. This is a conditional jump instruction where the contents of Cx is decremented by 1. Say when this instruction is executed, content of Cx gets decremented 1 by 1. Then microprocessor checks the content of Cx. If the content of Cx is equal to 0, then it comes out of the loop. If the content is not equal to 0, then microprocessor proceeds back with the iterative operation. It is something like this. Move AL comma 00H. Before this I load the count. Move CX comma say 100 or 1000 say, or okay, let me take it as 100H. Now increment AL, loop back. Now say what is the meaning of this? I have loaded Cx with the count, count is 100H, right? AL has got the initial value. So this initial value 0 getting incremented, the content of AL is getting incremented Cx number of times. Now if I want to repeat this operation, then I will be using loop back. So in this loop back, what will happen is, say first Cx will get decremented by 1. So if Cx is not equal to 0, that is if 0 flag is equal to 0, then say go to label back, else go to next instruction after loop instruction. So after this loop instruction, I may have something like move result comma AL. So if Cx is equal to 0 or till Cx is equal to 0, say AL contents is incremented. Once Cx becomes say 0, then when loop instruction is executed, so automatically say the control of execution transfers to the next instruction. So this is how your loop instruction works. In this simple example, I have given only one instruction here. You may have set of instruction which may be say repeated as per your program requirement, and you can give that. So that is how basically your loop instruction works. My dear students, remember loop is a special instruction in 8086 instruction set which works only on the content of Cx. It is mandatory that the programmer should load a Cx with the count value. Suppose if you ask me a question, sir, if I forget to do that, what will happen? Say absolutely your assembler will not give you any error. The reason is Cx may have some predefined or some garbage value. Say for that value your loop gets repeated so many number of times. So you should be very careful when you are trying to use these kind of programming features of 8086. Next, loop if equal to relative address. It is a conditional jump instruction where we try to check Cx, decrement Cx by 1, and if the Cx content is not equal to 0 and if ZF is equal to 1, then the microprocessor performs the jump operation by adding relative address to IP. If Cx content is equal to 0 or if ZF is equal to 0, microprocessor does not perform the jump operation. So loop say if equal say is the extension of loop instruction. Next, loop if not equal. It is again a conditional jump instruction where the contents of Cx is decremented by 1, then the microprocessor checks the content of Cx. If Cx content are not equal to 0 and ZF is equal to 0, then the microprocessor performs the jump instruction. Otherwise, say if Cx content is equal to 0 and ZF is equal to 1, microprocessor does not perform jump operation. So here two conditions are checked. One is Cx is equal to 0 and then say ZF is not equal to 1. So that is what we try to check with loop NE. Now from past 25 minutes we discussed about what is the conditional branch instruction and the different iterative control instructions. Now let us pass on to the important stage of instructions or important instruction concepts, that is what is called as calling a procedure. Say you call many procedures in your program, and writing a modular program is one of the best way of writing programs. Now let me just reiterate what is a procedure or a subroutine. Any program can be divided into smaller part, and each smaller part can be individually developed and tested. This approach simplifies the process of software development. So that is what is called as your modular programming. So writing functions makes your program more simpler to handle. And this technique is what is called as modular programming, where each smaller part of the module, say program, is what is called as a procedure. Now this particular graphics will be able to tell you how basically your program gets executed. Now this is the main program where I have n number of instructions in the main program. So in the middle I have also called the procedure, say after some instructions, say after instruction 0, instruction 1, I am trying to call a procedure, and then this is the next instruction followed by some more instructions, and then again I am trying to call a procedure, and so on and so forth. So in the main program, as usual, we are trying to call some procedures. Let us try to understand, say from this graphics, how basically we would be able to visualize the calling of a function. Now instruction pointer, as you know, will always point to the next instruction to be executed. Now instruction pointer is pointing to the next instruction to be executed, that is instruction 0, which will be stored in the code segment memory. Now say after execution of this instruction 0, what will happen? This instruction 0 will go to the instruction queue which is present in the bus interface unit. So automatically IP will be incremented to point to the next instruction to be executed. When the instruction 0 is getting executed, IP will be pointing to the next instruction to be executed. Now say after execution of instruction 0, say the instruction pointed by IP will be fetched in. Now IP will point to the next instruction, and the next instruction here is calling a procedure. I am trying to call a procedure. So to call a procedure, the instruction that I use is call. Call is an 8086 instruction used to call a procedure. Now IP is pointing to this instruction, which is a part of the main program, say when instruction 1 is getting executed. Now after execution of instruction 1, what will happen? Say 8086 will start fetching this instruction, and it fetches this call instruction. Once this instruction call is being fetched inside the bus interface unit for the execution, say IP will obviously point to the next instruction after the call instruction. Now the current instruction that is getting executed is a call instruction. When the execution unit tries to execute this instruction, it will come to know that this is a branching instruction, or I am trying to call a procedure. Programmer is trying to call a procedure. Now what will happen here? The control of flow of execution has to be transferred to this procedure. Now carefully observe. Now IP was pointing to the next instruction after the call instruction, say where the address of that next instruction is X. Let us assume that it is X. Now IP, say instead of pointing to this, as per the previous instruction which was a call instruction, IP will point to the starting address of this procedure 1. Now here there are set of instructions in the procedure. Now what is the concept? This procedure has to be executed, so there is a branching here. Now this procedure gets executed. Now at the end of every procedure we have something called as return. In your C language you use return. Here the equivalent instruction for returning the control back to the main program is RET. RET is an 8086 instruction used for returning the control of execution back to the main program. Now say when the return instruction is executed, what will happen? The return instruction goes to the execution unit, it gets executed. Meanwhile IP will be pointing to the next instruction in the procedure. Say there is nothing after this return because the control gets transferred from here, and this will not be however executed. But as usual IP will be pointing to the next instruction to be executed or the next location. So meanwhile return gets executed and the control say gets transferred, so that IP will come back say to the next instruction after the call instruction. Now if you carefully observe, so I was executing like this, I went here, say the control was transferred to procedure 1, it got executed, and we came back here. Now as usual these instructions gets executed. Now see this, there are two branches from main program to the procedure when the call was executed, and then when the return was executed in the procedure, again the branch happened back to the main program. Now as usual, the main program say gets executed with instruction 4, 5, where this instruction 4, 5, 6 are the normal maybe arithmetic or logical instructions, or a data transfer instruction where the branching will not happen. Now after the 7th instruction, again I am trying to call a procedure where I am trying to call another procedure, procedure 2 here. Now so when this call instruction gets executed, say meanwhile IP will be pointing to the next instruction, because IP will not be knowing what is the previous instruction, and this previous instruction will be decoded only in the execution unit. So IP will be as usual pointing to the next instruction. The previous instruction, since it was a call instruction, there happens a branching. So from here the control gets transferred to procedure 2, and now what will happen is IP starts pointing to the instructions present in the procedure 2. Now as usual, say the procedure 2 instructions gets executed one after the other sequentially, and then at the end I have a written instruction. So the control of execution will be again transferred back to the return address. So the return address here is Y. What is this return address? As you know, return address is the address of the next instruction after the function call, where the control transfer will happen when the execution of control comes back to the main program. Now carefully see this. I'll repeat. Now when return is executed, IP was pointing to the next location after return. So since it is a return instruction, processor tries to retrieve back the return address which was stored in dash. Where does your return address get stored? The return address gets stored in stack. So it is a default operation. So now IP will point to this return address and the instruction gets executed. Now if you carefully observe, there are two branches here. One, the execution gets transferred to procedure 2, and then the execution control will be returned back to the main program. Now here X and Y are the return addresses. MUP executes the instruction of the main program sequentially. So whatever that I have discussed now same thing is being iterated here. So the procedure gets executed, and once the return instruction is executed, the control of program execution is transferred back to the main program. Now coming on to the call instruction, what are all the different types of call instruction? As usual, the different types of call instruction includes the near call and the far call. As you already know the word near. What is the meaning of near and far? Say near results in intra-segment calls and far calls results in inter-segment calls. What do you mean by intra-segment and inter-segment? Intra-segment is if I am trying to call a procedure which is present in the same segment, then it is called as near call, and if I am trying to call a procedure which is present in some other code segment, then it results in a far say call, and it is an inter-segment call. Now under near call I have indirect and direct calls. Under far I have indirect and direct calls. In a nutshell, sir, what is meant by this indirect call and direct call? In direct call, you try to specify the address of the procedure directly in the instruction. In an indirect call, you try to specify the address of the called procedure using any register. So that is what is the meaning of direct and indirect. Here in the instruction itself, you directly give the address of the procedure. In the indirect case, you try to give it through a memory location, or you try to give it through a register. Now let us see one by one. How does this direct near call works? Call address, example, call fact, call 1234H. So here 1234H is the address of the procedure that I am trying to call, which I have mentioned in the call instruction itself. That is the reason why we call this as direct near call. So here it is a 16-bit signed number where the instruction is used for transferring the control of program execution to a procedure present in the same code segment. As usual, it is an intra-segment call. This instruction alters only IP and it does not alter CS. The basic reason is it is an intra-segment call. When it is an intra-segment call, CS contents will not be altered. Remember this very carefully. Here is an example. See this. Now, how does this work? When I say call 1234H or when I say call fact, say the control will be transferred to the procedure. Now, say after execution of the procedure, say the control will be transferred back to the main program. Now if you see this, the return address of the IP register is saved on to the stack by performing a push operation. Means when processor executes the call instruction, it will not directly branch to the target location or the procedure location. Say it first pushes the content of the IP. What does IP contains? IP contains the return address, or is the address of the next instruction. That will be, say, pushed on to SP. So first SP gets decremented by 2, then IP will be copied onto, say, the stack locations. The content of IP is modified to branch to the procedure by adding address to IP. So now what will happen is IP will be added with, say, the target location address or the relative address. So ultimately I get the starting address of that procedure, and that procedure starts getting executed. Now what is this indirect near call? Indirect near call is something wherein which we are trying to specify the address of the call instruction indirectly, where it can be given using a 16-bit register or a 16-bit memory location. So as usual, it is an intra-segment call. So let us try to understand with an example. Call BX is a good example for indirect near call, where the return address of IP register is saved onto the stack as usual. Remember this, when a call instruction is executed, you need not have to push the contents of IP onto the stack. By default, when call is getting executed, the first operation that is done by the processor is it pushes the current content of IP onto the stack. So to push the current content of IP onto the stack, say SP will be pointing to the top of the stack. So SP gets decremented by 2, then IP will be, say, pushed on. That is the reason SP gets decremented by 2, and then, say, IP will be pushed onto the top of the stack. Now IP will be added with, say, the address specified in the BX register, because here I am trying to specify the target, say, location address or the procedure location, procedure address, say, using BX register. So what will happen is, say, the contents of BX will be copied to IP. So IP will point to new location at which your procedure starts, and, say, processor will start executing the procedure from that particular location. Next, let us pass on to the for call. The first category is direct for call. Say call for ADDR. So what is the concept here? For is an assembler directive, say, where this assembler directive will tell the processor that, say, this particular procedure is not present in the same segment and this procedure is present in the different segment. Now by using this assembler directive, say, assembler, while converting this instruction into its equivalent binary, specifies the processor, say, delicately that, say, here, say, since this is a for instruction, both CS and IP contents are getting updated. So this instruction is used for transferring the control of program to a procedure present in some other segment. It is an inter-segment call. Both CS and IP contents are executed. Now carefully see this. Call for 1, 2, 3, 4, 5, 6, 7, 8. How many bytes are there? 4 bytes are there. That is a 32-bit address, say, where first SP is decremented by 2, say, the content of CS is copied onto the top of the stack, then SP is again decremented by 2 to the top of the stack, IP is pushed. Now if you carefully observe, since this is an inter-segment call, both the content of CS and IP are updated. So before updating the content of CS and IP, that CS and IP, say, has to be preserved somewhere, and that, say, preservation locations are obviously in the stack. So in a for call, in an inter-segment say, calls, we always push both CS and IP contents onto the stack and then load CS and IP with the appropriate target locations. So CS will be loaded with 1, 2, 3, 4H and IP will be loaded with 5, 6, 7, 8H. What do you understand by this? So it means that the procedure which you are trying to execute is present at a code segment, say, starting from 1, 2, 3, 4, 0H. Then for this, if you add this offset, it will take you to the starting address of the procedure present in the other segment. Now indirect for call. So something similar to the direct call, only thing is we try to specify the call address, say, indirectly. It is also an inter-segment call. Now carefully see this, same thing will happen. Only thing is BX is pointing to some memory location. See this, BX is a memory pointer. It is pointing to some memory location at which you have the starting address of the code segment, target code segment, and the offset value. Now say whatever the contents pointed by BX will be copied onto IP, and whatever the contents pointed by BX plus 2, say, will be copied onto CS. Now it is the duty of the programmer to load in the data segment, say, the offset value and the target code segment value, so that they are copied onto IP and CS. However, before updating the content of say CS and IP, say first they will be pushed onto the stack and then this updation happens. Now after calling I have to return. So after execution of the procedure, we need to return the control back to the main program. So return example is RET. This instruction is used for transferring the control back to the main program. The return address present in the stack is popped. So whatever the return address which was pushed during the call instruction will be popped. For an intra-segment call, only IP will be popped, say because it will be a near operation. Say for return, say what will happen is both CS and IP will be popped, because say during the for call, say both IP and CS was pushed onto the stack, and obviously that has to be retrieved back from the stack during the return instruction. The assembler directive will identify whether the instruction should perform a near or a far operation. Say that is what is very important. Now till now we have learnt various instructions starting from data transfer instructions till the branch control instructions. Now let us pass on to another set of say concept, say what is called as interrupts of 8086. In this particular topic, we will be discussing on two major interrupts. One is BIOS int 10H and DOS interrupt 21H. Now, what is basically we learn in this is we try to learn some of the functions of int 10H, say like clearing the screen, setting the cursor position, writing characters to the screen in the text mode, draw lines in the screen in the graphics mode, changing the video mode. And if time permits, say we shall also be say proceeding in this session with the DOS 21H, that is input characters from the keyboard, how to output characters onto the screen, and input and output of strings. Now what is this interrupt structure in 8086? Say int is an instruction in 8086 which always results in a for call. Now what is this interrupt? Say interrupt is something like interrupting the processor. Processor is executing a main program and I want the service of the processor. When I want the service of the processor, I need to disturb the processor. I need to send a request saying that processor, I need your service. So in that case, we use this interrupt. So 8086 basically has say totally 256 interrupts, where these 256 interrupts are numbered from 00 to FFH. So FF means 255. So 0 to 255 is totally 256 interrupts. So remember, the interrupt structure of 8086 supports totally 256 interrupts, and they are vectored interrupts. What is meant by vectored interrupts? They are numbered. So int 00 to int FFH are the range of interrupts that is supported by 8086. When an interrupt is called, say processor saves the content of CSIP and the flags onto the stack and goes to the subroutine associated with the interrupt. So it is something similar to your say call, but only thing is say processor is executing the main program. So when there is an int instruction, then the control is transferred to that int XX procedure, and this int XX routine or procedure will be executed, and I will have an IRET here instead of return, and then the control will be transferred back to say the next instruction after the int instruction. So something similar to your call instructions. Now only difference is all int instructions say results in a for call, but in a for call we don't say save the contents of flag register onto the stack, but in an int instruction, when int instruction is getting executed, say CS is pushed onto the stack, IP is pushed onto the stack, and flags are also pushed onto the stack, say so that when IRET is executed, all those three components will be taken back from the stack. Now say we shall start off with say the int 10H and int 21H, which are most widely used say interrupt instructions in 8086 programming. Now let us start with BIOS int 10H programming. What is this BIOS in 10H programming? My dear students, first of all, let us try to understand why these interrupt instructions are very much essential. Say you have your hardware and you need to access your hardware. Hardware includes your processor. Now, to interact with this hardware, one crude method is directly intervene or physically handle this hardware. If I physically handle the hardware, I will be losing the components, I will be losing this hardware. So, to avoid that, we will have above this the BIOS routines. And above this, we have your DOS routines, and then above this, you have your system programs, and above this, you have your user program. So, if I want to access the hardware, what is the hardware? Hardware can be your processor, your memory, your say hard disk, anything. So, your user program sends a request to the system software, and system software in turn sends it to the DOS, and DOS in turn sends it to the BIOS, and BIOS will help us in accessing the hardware. So, this is how basically say it works. So, hardware will return the value to BIOS, to DOS, then to the system program, then to the user. So, this is the user who is trying to work on the hardware. So, this is what is the background story behind why we need to use, or what is the need of using BIOS or DOS or any interrupts. Now, if I want to access the hardware of the computer, so I need some delicate methodology, and the delicate methodology is above the hardware. I try to have the BIOS functions. Using the BIOS functions, that is basic input output setup functions, I would be able to access the hardware. Now, say above BIOS, I have the operating system, where that operating system may in turn call some BIOS functions. So, that BIOS functions in turn help in accessing the hardware. Above this is what is your system programs, like your editors or your compilers or whatever it may be. So, and then you have your user program. So, I write a program as a user, or you write a program as a user, and in that user program you will call some say system program functions, and that system program functions in turn say internally calls a DOS functionality or a function, and this DOS function internally may call a BIOS function, and then it may help us to access the hardware. Now, if you see this previous slide, see this here, clearing the screen. What do you mean by clearing the screen? Setting the cursor position. I am trying to access the hardware. Screen is the hardware. So, I am trying to access the hardware without touching the hardware. So, that is what is the strength and speciality of these interrupts. So, in the syllabus, we will be discussing on two most widely used interrupts, that is in 10H and in 21H. So, in 10H, we will be discussing about clearing the screen, and then we will continue with how to say work with cursor positions, how to change the text mode, how to change the graphics mode, and then what are the video modes that we will be able to work upon. Now, using this, says carefully observe, we are trying to handle the screen characteristics or screen attributes, and we are able to make changes in the screen attributes as per our requirements. My dear students, in the today's session, we started with the conditional branch instructions. We discussed about various conditional branch instructions. Under conditional branch instruction, we discussed about some of the instructions for signed operations, and some instructions work for unsigned operations. We also discussed about some of the conditional branch instructions which works for say flags, particularly jump if 0, jump if carry, jump if sign, jump if overflow flag, jump if no overflow flag. All of them work with the conditional flags. Then later on, we discussed about the iterative loop control instructions like loop, loop if equal, loop if not equal, where whenever you want to repeat some of the operations say iteratively, then we go for this looping instruction. What is the fundamental there? The fundamental there is, before using a loop instruction, you should load CX with the count value or iteration count value. Without doing that, say your loop may go havoc. So, it is mandatory to load CX with the say the count value. Then later on, we also discussed about the concept of say the call instruction. So, what are the call instructions? How do they work? Say what is a near call? What is a far call? In near call, what is direct, what is indirect, and in far call, what is direct and what is indirect was also discussed, and we winded up with say the return instruction. Now say I have given you the introduction for the concept of interrupts. You should never forget this. Say the basic concept of your BIOS function interrupts or DOS function interrupts say will help us in say interacting with this say underneath hardware of your say 8086 PC or any PC as a matter of fact. For that say we try to call those functions in our program. So by calling those BIOS or DOS functions or DOS interrupt functions in my program or the user program, I would be able to access the hardware without touching the hardware. And that is what is the speciality and importance and need of interrupts. In the next class we shall proceed further with say the BIOS and DOS interrupts, and we will wind up the module 2 with discussion on interrupt structure of 8086. Thank you very much.